Hello everyone, I'm Takuya Suzuki from Obayashi Corporation. Thank you for the opportunity to speak here today. I'd like to talk about the unique geological risks in Japan and countermeasures adopted. I will take the Yoshinomoto Highway Tunnel for example. In addition, I'd like to briefly introduce the latest technologies in tunneling we Obayashi is now tackling. First, I will briefly explain the geology of Japan. The Japanese archipelago consists of 4 plates, and Japan has extremely complex geological structures. As the oceanic plate subducted under the continental plate, sediments on the oceanic plate was scraped off and added to the continental plate. The added sediments are called an accretionary prism and have very fragile geological features. This slide shows the outline of accretionary prism. The subduction of the oceanic plate pushes sediments on the land. This part is called an accretionary prism. Most of the Japanese archipelago is made up of this accretionary prism. In some regions, you can see the terrain raised by these forces. These photos are geological conditions observed at the face of the Yoshinomoto Tunnel. The left side photo shows alternate layers of sandstone and shale. You can see the inclined sedimentary structure. The right side photo shows the layer crushed and mixed by the excessive pressing force. This slide shows the geological outline of the Yoshinomoto Tunnel. The geology consists of alternate layers of sandstone and shale and their mixed layer. Due to the fragile geology, there were several landslide marks around the tunnel. Initially, excavation started from the north portal in 2007. The construction was difficult due to the ground load more than expected and landslides. As a result, construction began on the south portal in 2015, where Obayashi Corporation was in charge of excavation. In the initial plan, it was confirmed that there was a small landslide block on the north portal side. However, when excavation started, a large landslide was induced at the location indicated as Block A in the figure. After that, landslide blocks from A to E were detected by the radar survey. Furthermore, during excavation, the tunnel displacement increased, and the inboard struts were deformed. The face stability was impaired, and the tunnel face collapsed several times during excavation. Therefore, the excavation of the pilot tunnel was planned in this survey section prior to the main tunnel. The purpose of the pilot tunnel is the monitoring of the landslide blocks A and B and geological investigation. Based on the results, the support structure was modified, and early closure of the tunnel section and auxiliary methods were adopted. In addition, excavation of the drainage tunnel and drainage borings were conducted to prevent the landslide. This slide shows the situation during the pilot tunnel excavation from the north portal. The red dotted line indicates the area where the large landslide occurred. Next, the support structure was redesigned based on the results of the main tunnel and pilot tunnel excavation. A frame analysis was adapted to examine the support structure. The working load mode is reproduced from the displacement measurement results, and the magnitude of the ground load was estimated from the stress measurement results of shotcrete and steel support. Then, the support structure was selected, which is acceptable for the reproduced ground load. As a result of analysis, it was confirmed that the stress was locally concentrated at the corner of the steel support and greatly exceeded the yield stress of the steel support. Therefore, the cross-sectional shape was changed to a shape close to a circle, which has mechanical advantages, and the stress concentration was relaxed. This slide shows the redesigned support structure. The thickness of shotcrete is 215 millimeters, and the compressive strength is 36 Newton per square millimeter. The length of rock bolt is 6 meters. A deformation allowance of 100 millimeters is provided to ensure the required inner cross-section after deformation. To restrain the deformation, early closure of the tunnel section is conducted by installing the shotcrete and invert struts. Next, I will explain the construction sequence. Step 1. The excavation method was full-face method with auxiliary bench cut. The tunnel section was closed early at 8 meters away from the face. Step 2. The length of excavation was 1 meter, and after 2-cycle excavation, early invert closure was performed, then this cycle was repeated. Step 4. Auxiliary method was applied every 9 meters of excavation. Pipe for piling and long face bolts were adopted. Step 5. In the section where landslides were concerned, a pilot tunnel was advanced at the center of the main tunnel. Step 6. After that, the excavation proceeded while widening the top heading and passed the section. Next, I will explain the measures taken for the landslide blocks C and D sections. Although it was considered that these landslide blocks would not directly affect the tunnel, it was necessary to minimize the effect of tunnel excavation so as not to activate the landslide, because there was a village around Block C. For this reason, the tunnel alignment was shifted to the west by a maximum of 100 meters, so that the distance between the landslide surface expected for Block C and the tunnel could be secured in 30 meters. Regarding the support structure and the auxiliary method, the above-mentioned pattern was continuously adapted. Finally, I will explain the measures for the landslide block E. In this section, direct landslide countermeasures were necessary to ensure the stability of the tunnel. Because excavation from the south portal passes through landslide block E. Since there was a valley topography near the south portal, an embankment of 600,000 cubic meters was carried out from the bottom of the valley to the height of 60 meters. Furthermore, a counterweight field was adapted in front of the south portal. Before the excavation of the main tunnel, the pilot tunnel was advanced to monitor the landslide behavior and to investigate the geological conditions. The support structure and the auxiliary methods were adapted as same as the results of the north section. This slide shows the situation during the excavation of the pilot tunnel from the south portal. The red dotted area indicates the embankment with the valley backfilled. This is a photo from another angle. We adapted reinforced embankment with steep slopes at various places to early start the tunnel construction. This slide shows the situation of excavating the main tunnel from the south portal. Excavation was performed with a large breaker and a backhoe. Blasting was not adapted because it may loosen the ground. Marking was done with a large wheel loader and large dump trucks. This photo shows the erection of steel supports by using a shotcrete machine with erection booms. You can efficiently perform shotcrete and erect steel supports without replacing the machine. To install the lock bolts and auxiliary method, a drill jumbo with 3 booms and 2 baskets was used. Recently, due to technological advances, automatic drill jumbos have been gradually used in Japan for rock bolting. At that time, a normal drill jumbo was used at this site. This photo shows the installation of invert struts. In this way, the tunnel construction was completed. That's all I have to say about the excavation of the Yoshinomoto Tunnel. I'm glad if you can use it as a reference. I'd like to move on to the next topic. I will briefly introduce the latest tunnel technologies, which we are now tackling. First is the tunnel phase evaluation system by AI. This technology makes use of deep learning from the acquired tunnel phase image and makes it possible to use AI to perform evaluation equivalent to that of geological experts. Evaluation items include weathering alteration, fracture spacing, fracture condition, and strength. Because it is cloud-based, you can use it anywhere, as long as you have internet environment and a terminal such as a tablet. It is possible to compare the visual evaluation results by the site engineer and AI on-site. Next, I will introduce a technique for expanding the results of drilling exploration using a drilling jumbo to 3-dimensional contours. This is to predict the properties of surrounding rocks using geostatistical methods from the information obtained from the 3 drilling logs. The contour represents the hardness or softness information of the ground. This makes it easier to understand geological conditions ahead of the tunnel phase and helps to determine the countermeasure at one early stage. The above-mentioned rock mass information will be integrated into CIM. CIM is an abbreviation for Construction Information Modeling, which integrates information from the design stage and records obtained during construction into a 3D model. The purpose of CIM is to improve the productivity of construction and subsequent maintenance. We always make use of CIM for conference with clients, such as changing the design of the tunnel support structure. This photo shows the appearance of the web conference. Previously, the contractor and client hold a conference at site, but we are currently trying to get the client to join the conference from remote locations. This will be possible by establishing a Wi-Fi communication environment inside the tunnel and using smart devices. You can upload construction information, such as CIM, to the cloud and share information even in remote locations. Since it is possible to participate in the conference without going to the remote site in mountainous areas, it has been well received by the clients. That's it. Thank you for your time.
Thank you, Mr. Takuya Suzuki, for your presentation. I am sure many of you are keen to know more and would like to engage in dialogue with our speakers today. For today's symposium, we will be taking in questions from participants via the Q&A function at the bottom of your Zoom interface. The speaker will answer the selected questions either during break or at the end of the event. May I now invite Mr. Yuma Shinaga to deliver his presentation on features of urban ring method adopted for construction of underground structures. Mr. Yuma Shinaga is currently studying ground freezing techniques for the purpose of ground improvement and water stoppages. Please welcome Mr. Yuma Shinaga.